We have studied the fundamental of graphene, properties of graphene, and then graphene synthesis. Then also we are aware about graphene transfer from one substrate to the another substrate. And then recently we have talked about the synthesis of graphene nanoribbon, in which we were particularly talking about how we can prepare a nanoribbon by cutting the CNTs. And we have demonstrated various tools by cutting the CNT and to get the the graphene nanoribbons, right? So we are aware about graphene synthesis and transfer, but how to be sure whether the grown material or the synthesized material is graphene or graphene oxide or its derivative? So understand this, we have to do the identification and the characterization of graphene. Therefore, today I am going to talk about how we can identify whether it's graphene or something else, and what are the characterization methods or tool can be used to do the graphene characterization. So first of all, we can start with microscopic methods, so which is well known, and I think we have already discussed earlier in our talk when we are talking about the nanomaterial characterization. So these are the same tools. So I'm not going to talk about detail in this tool. Our concern will be how these tools can be applied to characterize the graphene and graphene oxide and its derivative. So we can say we may use scanning electron microscope. We can use transmission electron microscope, commonly known as SEM and TEM. Okay, and where we can get the idea about what kind of growth of graphene is there and what kind of surface morphology is there. We can also do the atomic force microscopic analysis or scanning tunneling microscopic analysis to get more clear cut idea about morphology, the size of graphene, the thickness of layer, the number of layer, uniformity of the layer, etc., and some electronics and properties. Similarly, there are other tools, can say it's spectroscopic tools, which are commonly adopted for characterization of graphene. The well known is Raman spectroscopy, where we can identify the graphene sheets, how many layers are there, as well as what kind of defects are associated within. FTIR is another important tool which can be used to understand the functional group in graphene and graphene oxide. Similarly, UV visual spectroscopy, we can understand if there is any band gap, is there any absorption of light, and then we can have a differentiation between graphene, graphene oxide, or reduced graphene oxide. Similarly, XRD, we are already aware, we can get the idea about crystalline phase, etc. XPS, you can have idea about surface chemical composition, what kind of bindings are there. Next are NMR, can get understanding about hybridization, whether it's sp2 hybrid material or there is still some sp3 hybridization. Similarly, DLS or DPI. So these are commonly used tool in case of graphene. Next, we can switch to our optical analysis, particularly optical absorption and nonlinear Kerr effect. Photoluminescence, if there is any emission is possible from graphene, and optical band gap calculation. If it's not pure graphene, it is having some kind of bonding or some kind of functionality, right? Similarly, in mechanical properties, many things are there, such as Young modulus, Poisson ratio, surface tension, or maybe the gas leak rate, or maybe the tunneling of hydrogen atom through the graphene sheet. Next, we can say thermal properties and thermal effect. So, of course, thermal conductivity of graphene, and then how graphene is stable at different temperatures. So, we can see the thermal stability that can be measured by TG analysis. In electrical properties, mostly we look for conductivity, mobility, and spin transport. Also, electrochemically, we can understand the reduction and oxidation potentials. We can also understand the carrier concentration by quantum Hall measurement, work function of the graphene. So these are the common tools. Now we will get one by one in slide details. So the first tool is scanning electron microscope of graphene. So it's well-known tool, and by using SCM we can get variety of information. As we have already discussed earlier, we can get the idea about topography, surface feature of an object, morphology, basically the shape and size of the graphene. Similarly, the composition. If we are having EDEX attachment, we can get what kind of elements and compound or the crystalline information is there. Similarly, by using EBSD, we can also get the crystalline structure and crystalline orientation. So here I would like to share one SCM data of graphene, and then graphene was grown on the copper substrate, where substrate were treated in three different way. If you see here, the first sample, which is non-treated graphene. Substrate basically is copper, and copper was not treated. It's directly the growth of carbon was, graphene was done. The second one is when copper substrate was treated with HNO3, and then the growth of graphene was done. And then the third is when the copper substrate was electrochemically polished, and then the growth of graphene was done. And you can see the three clear-cut differences are there in their morphologies. See, if you can see here, this black color in picture A, it look like something growth is here, 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 here. Then some growth is here. Then some growth is here in this region, in this region, in this region. So what would we say if we are using without treating the substrate, just thermally clean because we are using very high temperature, then the graphene growth is an irregular shape. See, there's no regular shape in the graphene. While in the second case, when the nitric acid was used to treat the copper substrate, and then of course the thermal treatment is there, then we are going to get little bit hexagonal shape. So few hexagon and then some irregular. See this area is all irregular, something random. But see some pictures, it is having some kind of hexagon shape, not exactly, but look like something kind of hexagon, right? So there are few hexagon and then some random growth is there. But see how beautiful in case of electropolished substrate, we are having a large regular hexagon shape of the graphene. See the graphene sheet is look like clear hexagon format, and its size is also almost 3 micrometer. So SCM is a very important tool to understand what is the size of growth, what kind of morphology of the sheet, and we can also get some idea about their thickness, but not exactly what kind of thickness we cannot get. Maybe the contrast can give some idea. So this is the one tool. Next, we can use the transmission electron microscopy to analyze the graphene or to characterize the graphene. And TM is also the system which is based on the electron wave. And here we can get a clear-cut idea about the number of layer which has been in case of graphene sheet. Similarly, we can also get the clear-cut idea about the crystal structure of graphene. Here one example is there. If you see the picture A, so this is copper grit. So these are the copper grit and this is the base. So here we are having all entire area covered with the graphene layer. monolayer. See this region, if you are able to see this region, let me try it, something like that. See this region, it is look like little bit darker. So this is maybe the folded region, or where we are having a two-layer graphene. So though by doing TM analysis, we are not able to see very clear whether the sheet is there or not, because the sheet thickness is very less, and if that much less thickness is there, we are not going to get any contrast. And the other point is, I think the entire surface is covered by the sheet, so we are not able to see any contrast except the region which is folded here, right? Now the selected area electron diffraction pattern is recorded, and you can see in the figure B here, the electron diffraction pattern, and we are able to get 6 very clear cut spot. See, 1, 2, 3, 4, 5, and 6. And if you draw a line across them, they form a perfect hexagon. So that selected area electron diffraction pattern shows this is a monolayer, because these are the single spots and dots are there, and then these are the secondary. So this is basically first Brilliant zone, and by using this analysis we can clearly indicate that the growth graphene is monolayer, and here basically it's a graphene oxide sheet. Okay. Similarly, the reciprocal length versus intensity can be plotted, and we can get the intensity of respective planes. See in figure D. In figure D, basically we are having a bilayer graphene oxide. We are having 2 overlapping layers, and it is also cover entire surface. And if you see, there is something here which may have little bit higher number, maybe 2 or 3 layers. So when the selected area diffraction is recorded, see the picture E. See, we are getting 2 points together. See the point 1 here and the point 1 here. So 2 point with then 2 point together, then these 2 point together. So this is the second point, this is the third, this is the fourth, this is the fifth. Maybe it's not getting proper aligned, so that's why 1 point is visible, but it should be 2, and this is the sixth. So basically total are the 12 points. 12 points, so 6 point indicate for single layer, and then another 6 point is indicating the another 1 layer. So that is basically we are having a bilayer or 2-layer graphene oxide. So we can get the idea like monolayer in case of A, bilayer in case of B, just by doing the TM analysis. See the selected area diffraction of grid, some region of here. So you can see it is showing the polycrystalline nature, and therefore we are getting a circle spots which are forming a kind of circle. So it's not a single crystal, it's a polycrystalline material. Now let's see another example of TEM. We are having a gold coated carbon support and then multiple graphene oxide sheet. So they have recorded the selected area electron diffraction pattern at position B and also at position C. So position B is the grid which is coated by the gold, and position C is our multi-layer graphene. See, even if you see this picture, nothing can be visible. It looks like nothing is, no material is there. However, if we are doing selected area electron diffraction, then we can get a very clear-cut indication of the graphene growth. See the first, again here we see this dot with this form of circle which shows the polycrystalline nature of gold pattern. And in case of C, again if you see there is a lot of point 1, then 2, 3, 4, 5, 6, 7, then 1, 2, 3, 4, 5, 6, 7, 8. So it's little bit difficult to understand unless we have multiple data set, but as indicates like there is not a single layer because it's not single crystal. There are multiple layers which are having layer by layer structure 1, 2, 3, 4 like this way. And when we are scanning it, so though one is giving the hexagon, let's say something like that 1, 2, 3, 4, 5, 6, something like this hexagon. But once we are having multiple layers, then it's forming a kind of circle. So which proves like at this region there are many layers in graphene. Similarly, in the D picture, if you see here, again there are few layers in this region, and this is the region where we are having the carbon. But this layer is relatively less in number as compared to the first case. So if you compare the electron diffraction, so E is as usual, since this is a little bit thinner and we are able to get the more peak for gold, but still it shows the polycrystalline nature as similar. Our area of interest is F. So in case of F, if you see the peak 1, 2, 3, 4, 5, 6, 7, 8, so it's not very regular because this is not uniform. Maybe some other folds are there somewhere and some in other region, some interface is there. So we can say this is of kind of few layer, 2 or 3 layer graphenes are there. So if we analyze the graphene by doing TM, we can get at least idea about how many layers are there and what kind of crystal structure is there. Further, if you see the TM image, here we are having the high resolution TM image of graphene oxide. See how beautiful this image is. You can see clear cut each atoms, how these atoms are there, and these atoms are having the high magnification of zoom area here. So this is the first zoom area. This is another area which is zoomed here. Okay. So if we closely look all this structure, they are having a hexagon format. See the atoms 1, 2, 3, 4, 5, 6. Form the hexagon, beautiful hexagon. Here also 1, 2, 3, 4, 5, 6. So all are hexagon. Similarly here also we are having exactly hexagon 1, 2, 3, 4, 5, 6. So means this is perfect hexagonal structure. However, see some atoms are having slightly blank spot. See the region here. See this region. See this region. See this region. See this area. This area. These all are defect. Where there are some vacancies or some voids are there. So though graphene is there, which is having clear cut hexagon format with some crystal defects. So we can also say by HRTM analysis, we can get the atomic arrangement as well as we can also get the idea about what kind of defects are associated here, right? Let's see the next example. See here clear cut difference when we are doing a cross-sectional TM analysis. So figure A shows the monolayer graphene. If you see this area, the layer, so this is shown basically a single layer of graphene. Similarly, this cross-sectional image, it shows bilayer. If you see these two deep area, one and then another, one area and then other area. So these are, you can see the two layer of graphene. Also FFT, you can see this, and you can measure the basically the distance between these two. So we can get the idea what is the gap between the two layers. We can also measure the thickness of the layer, right? So these kind of information we can get from TM analysis. Similarly, see here, this is having a 3-layer material. You can see the 1 layer, 2 layer and 3 layer. Here again you can see 1 peak, 2 peak, 3 peak. related to the three-layer graphene. So number of layer can be also identified. So TM is also very useful technique for the number of layer analysis and with the crystalline structure analysis. Right. Now we'll move to the other technique, which is known as the atomic force microscopy, which is also very useful. Even I utilize this technique a lot to analyze the graphene nanoribbon. And as I discussed earlier, this technique is particularly based on the interaction between sample atoms to your tip atoms. The force could be van der Waals interaction. So there is different mode of analysis. You can go for contact mode or the tapping mode or something else. So generally we are doing in tapping mode analysis, and data is very informative. Here you can see one set of data. So we can get the information about morphology, thickness, again the uniformity of the layer, the number of layer that can be measured. And one more important area is sometimes we are growing the sheet which is having some micron size, let's say 10 micron, 20 micron, 30 micron, and that morphology of that site, that dimension may be not very visible in case of SCM or TM. So AFM is more useful if you are having a large sheet dimension, sheet depth. That kind of information we can extract by using the atomic force microscopy. Here you can see one height and phase image of graphene nano sheet. So first off, if you can see the scale here, scale is 5 micrometer, which suggests like this picture is could be 20 by 20 micrometer size, and then your sheet size is almost this much, which we can say it's almost 10 to 15 micrometer size. And what kind of information we can get? So we can see here the overall morphology of this sheet, the dimension of this sheet. Also, if you see here these lines, right? If you want, I can make like this is one line. So, sorry, these lines basically indicate the wrinkles in graphene, and here we would like to see what is the thickness of that sheet. So a line scan has been done. So see from here to it's look like this is a noise. This again some noise due to the wrinkles, and then this is the base. So basically we can consider the base of this substrate and then height of this. So this is again almost 0 and 1 if you compare. Or this phase image you can see here. This is phase image. So this is almost 1 nanometer thick. So this is the image when we having a graphene oxide, and when the graphene oxide was reduced, so surface functional group is removed, and now if you see the height profile, see the same sheet, it is reduced. Now almost this height is very less. It is almost 0.5 nanometer or 0.6 nanometer. So we can say that after reduction, the height is reduced, and this is a monolayer of graphene. Here is another picture. You can see figure A and figure C. So figure A is graphene oxide, and figure C is when we have reduced the graphene oxide. So the same area, this is the zoom of this area only. The previous pictures, if you remember, they have basically measured the thickness. So this is look like kind of uniform monolayer. So they have scanned one line here that you can consider the up and down as compared to the base, and this is within the substrate. So what kind of foldings are there, basically the roughness of the sheet. And this is the blue color correspond to the variation in the height, and this is the red color which again shows the variation in the height. So sheets vary from -1 to +1 when this is graphene oxide, right? And you can see the gap. But see the things when it is reduced, this green color is having very less height, and even this red is also varying from 0.5 to almost 0.5. So you can see the height is reduced, the thickness of the sheet is reduced when it is reduce the graphene oxide and form the reduced graphene oxide. Okay. Now we move to the another technique, that is scanning tunneling microscope. So as its word suggests, it's a tunneling. So it's a quantum mechanical phenomena, and the principle is simple and almost similar to the atomic force microscope. We have the sample substrate and one tip. So there's an interaction between these two. If we are, let's say these tips are very close to each other, and if we are applying any potential and if there is any possibility of electron tunneling from atom of tip to the atom of the material or substrate, then we can consider this a tunneling effect. So based on the up and down, basically the topography, if you are having a fixed tip height, the number of electron which is tunneling may vary, or maybe can make a fixed number of electron, then movement of the tip will be there, or there will change in the current basically. So any of the signal can be monitored or measured, and then we can generate an image. So TM is also very useful technique, and many physicists use that TM to analyze many electronic property of graphene. I can write few, let's say the imaging the surface at the atomic level. Means we can get the atomic arrangement very clear and clean. We can get the hexagonal structure very easy. Information about electronic structure, mapping about the local density of state as the function of energy, number of graphene layer, and graphitic carbon in the large number of layer can be distinguished. There is many number of graphitic layers are there. See here one image. Figure A is having a 3-layer graphene. See the layer 1. This is layer 2. And this is layer 3. So see, if we focus only this area, see the picture here, this area, and then measure the height profile similar as we can measure in AFM. So we can get this kind of data, and these data shows what is the height. So height is almost 0.35 nanometer, right? So this is very less, and this is almost equivalent to the monolayer height. If you see these images here, so these images are perfectly reflecting the atom of carbons, the atom of carbons, atom of carbon, atom of carbon, atom of carbon, atom of carbon. So all are very beautiful honeycomb structure, and they are forming the hexagonal like this, like this, like this, 4, 5, and 6. Or maybe the another image data, atoms, atom. So a beautiful honeycomb hexagonal structure of graphene can be visualized by STM analysis. Similarly, we can get also some electronic properties information as I discussed. The simple thing, if we just measure the change in the current, and let's say we are having a sample where there is one region is single layer and the other region is having a 2-layer. So how this interaction between layer to layer in case of B is going to give different electronic properties as compared to the single layer. So figure A, the top one, this is basically shows the change in the current profile in case of first when we are applying a voltage. So see at top panel the tunneling conductance for graphene is in V shape and vanishes at dp. See, it goes to almost zero here. A typical spectrum for monolayer graphene, right? You know, like in case of monolayer graphene, we get almost zero conductivity. In case of K point, Dirac point. But when we are having a two-layer, bi-layer, see the bottom panel. Though the nature is similar, we are getting almost similar nature, but we are not having a zero conductance here. Why? There is some conductivity at the K point also, because there are pi-pi band interaction. And if you see the case of graphite, so this is look like a red, very huge gap because there is a multiple layers, right? So these kind of electrical properties can also be extracted by using STM analysis. So I hope I finished these two or three topics. Today we just talk about how we can use scanning electron microscopy to analyze the graphene, how we can use TEM and what kind of information we can get, and then AFM and then STM. And all our technique can be used to understand the particularly the thickness of graphene, the morphology of graphene, and the crystalline or the crystal structure of graphene. So now I will stop my discussion today. Thank you very much. Thank you.